Welcome, ladies and gents, to another flipped lesson. Today our focus is going to be on the idea of an empirical versus a molecular formula. And we want to get two things out of this video. The first thing is we want to understand the difference in the definition between these two words. The second thing we want to be able to do is to understand the steps that we need to calculate an empirical formula. We're going to do two examples in this video of how to do those calculations, and we'll follow up with a few more in class with a lot of practice tomorrow. Now, I am going to color code my math. I'm going to be using blue, green, and purple today, so I encourage you to do the same in your notes. All right, let's get started. So the first thing we want to do is understand the difference between molecular and empirical formula by definition. So if we're looking at a molecular formula, what that means is it's your actual formula. Oops, let me go back a slide, sorry about that. It means it's your actual formula. So it tells us the exact number of each element in the compound. If we compare that to an empirical formula is going to be the lowest whole number ratio of elements in that compound. So if you want to think of it in terms of math, a molecular formula is your non-reduced version. An empirical formula is going to be your reduced version. So let's look at a couple of examples. If I look at this first guy here, H2O2, what that molecular formula is telling me is that this compound has two H's and two O's. So that is the real life formula for hydrogen peroxide. If I wanted to take it to an empirical formula, I want to look at this compound and see if I can reduce it down at all. Since both these numbers are divisible by 2, I can reduce it from H2O2 to HO. So the molecular formula tells us exactly how many elements we have present in the compound. The empirical formula just tells us the ratio of the elements. So this is actually what's super useful for a chemist. This is more what we use in kind of experimental research. So let's keep moving on with our examples. If we look at both these examples, C2H2 and C3H3, we see that we can reduce them both down. And in this case, they're both going to reduce to the same empirical formula, which is CH. And that's fine. A lot of your molecular formulas are going to be able to be reduced down to the same empirical formula. So you just have to see what they're both divisible by. So this one I can divide them both by 2. This one I can divide them both by 3. Now if we look at this guy here, he should be familiar to you. This is water, H2O. If we look at this compound, he can't be reduced any further. So his molecular formula and his empirical formula are going to be the same. So it is possible to have something that cannot be reduced down any further. And when you have molecular formulas, they're not always going to reduce down to a 1-to-1 ratio. It is possible to get other ratios. If I looked at this guy here who's glucose, C6H12O6, all these elements are divisible by 6. So it would reduce down to CH2O. So on a test or a quiz, if I'm asking you to give me the empirical formula from a molecular formula, this is all I'm asking you to do. Can I take the molecular formula that's given to me and reduce it to anything simpler? So those are the easy types of problems. Let's talk about the guys who are a little bit more difficult. This is where we actually do some sort of lab and get data that we have to use to calculate the empirical formula for a compound. So what would be an example of this? As a chemist, I can go out and I can start digging in the Earth's crust. And I can get some sort of chunk that I may or may not know the composition for. I can take it into my lab, I can do some really complex analysis, and what that analysis is going to kick out is a bunch of information. And I can use that information to calculate the empirical formula. So I did an experiment where I was digging around in the Earth's crust and I found some compound. That compound had 39.6 grams of sodium, 27.6 grams of sulfur, and 41.3 grams of oxygen. That's what I got as my data. What I need to do is I need to convert these things into something that I can use to determine the empirical formula. Now when we talked about the mole map, we learned that the subscripts of a compound represent how many moles of that element are present. So when I look at H2O, that formula tells me that I have 2 moles of H for every 1 mole of O. So when we're doing empirical formula problems, what we have to do is take the grams that are given to us and turn them into moles. And that's going to be our first step. So we're going to calculate the number of moles of each element using molar mass. And you may have guessed that, yes, I'm doing this step in blue. So what does this step look like? What you're going to do is you're going to start with each element in the order it's given to you, and using your periodic table, you're going to go ahead and calculate the number of moles present using the molar mass. So my first element that I get to in my problem is sodium, and it tells me that I have 39.6 grams of sodium present in the compound that I discovered. So I can use the molar mass to go ahead and turn it into moles. I look at my periodic table and I see that it's 22.990 grams of sodium for every 1 mole. In order for my units to cancel, I have to put my grams on the bottom, and I put my moles on top. My grams cancel, and I do the math in my calculator. Because I'm starting with 3 sig figs, I need 3 sig figs in my answer, so I would have 1.72 moles of sodium after that calculation. I'm going to do the exact same process with my sulfur and my oxygen. From the problem, I know I've got 27.6 grams of sulfur. I look on my periodic table to see that 1 mole of sulfur is 32.065 grams. Again, my grams go on the bottom, so they cancel. I have 3 sig figs in my starting number again, so I need 3 sig figs in my answer. So when you do this in your calculator, you'll see that it's 0.860 moles of sulfur. The last element in my problem is oxygen. I found a compound that had 41.3 grams of oxygen. From my periodic table, 1 mole of oxygen is 15.999 grams. Again, my grams go on the bottom, so they cancel. I have 3 sig figs to start again. So when I do it in my calculator, I get 2.58 moles of O. So what these numbers are representing is the number of moles we have present in that compound. So I've got Na that has 1.72 moles, S that has 0.860 moles, and O that has 2.58 moles. So I'm almost there. The only issue is when we look at a chemical formula, I can't have decimal places as my subscripts. I have to turn these things into whole numbers. And that's where step 2 comes in. And I'm going to do this one in green. In step 2, what we're going to do is we're going to create a ratio. So we're going to divide each number from step 1 by the lowest number calculated to determine the subscript for our compound. So what is this step telling me to do? Divide each number from step 1 by the lowest number calculated to determine the subscript. If I look at the math I did in step 1, I can see my lowest number is 0.860. So I'm going to divide every single number from this step by that 0.860. The reason I do that is because when I do this math, it gets me to the number 1. So I'm setting up a ratio. If 1 sulfur is 0.860 moles, I can go ahead and divide the rest of these by that same 0.860 and figure out the ratio to my other elements. So I take 1.72 and divide it by 0.860. And when you enter that in your calculator, you're going to see it gets you to the number 2. We're going to do the same thing with oxygen. And when you do that in your calculator, you're going to see it gets you to the number 3. So what this is telling us is our ratio. For every 1 sulfur, I need 2 sodiums and 3 oxygens. So these numbers now become the subscript in my formula. So my formula would be Na2SO3. I don't need to put the 1 there because the S implies that there's 1 present. So this would be my final answer, Na2SO3. Now, in this problem, we were done at step 2. Not every single empirical formula problem is going to make it all the way to step 3. Only some of them will. So you can be done after step 2 if these are all whole numbers. Step 3 comes into play if these are not whole numbers. So if number 2 isn't a whole number, what you're going to do is you're going to multiply all of the numbers in step 2 by the same number to make whole number subscripts. That word is subscripts over there, by the way. That's kind of jacked in there. Sorry about that. This step can be very confusing. What we're trying to say here is, hey, if these aren't whole numbers, I can't have a decimal place of a subscript. So I need to find a number that I can multiply them all by to make them a whole number. This example didn't have that issue. Our next example will. So I'll explain step 3 in more detail with this problem. Now this problem is set up very similar to step 1, except this time it's actually talking about lab data. So this is going to be very, very similar to the lab we're going to do later in the week. This problem is a little bit more difficult because we have to be able to read and pick out what the information is telling us. So in this problem, a 0.3546 gram sample of vanadium metal is heated and reacts with oxygen in the air to reach a final mass of 0.6330 grams. Calculate the empirical formula for this compound. So when we're looking at this problem, we've got 2 different masses, and we have to be able to understand what they're telling us. This first mass is telling me, hey, this is how much vanadium I reacted. The second mass is telling me, hey, this is my final mass after I reacted with oxygen. So this mass right here, this 0.6330, is actually my mass of my vanadium plus my oxygen. So I have to do a little subtraction to figure out how much oxygen I actually have in my compound. So unlike the first problem, all my masses aren't directly given to me. I do have to do a little bit of math to get me to my mass of oxygen. So this is where we're going to take our final mass and subtract our vanadium to get our mass of oxygen. So we're going to do this 0.6330 grams, which is our vanadium plus our oxygen, and we're going to subtract those 3546 grams, which is just our vanadium metal. The remainder is going to be just our oxygen. So when you enter that in your calculator, you get 0.2784 grams of oxygen. So now we have our grams of oxygen and our grams of vanadium metal, so we can do the steps we just talked about. Our first step, turn those things from grams into moles. I start with vanadium because he comes first in the problem. You always start with the element that comes first in the problem. Vanadium is element number 23 on the periodic table. So when you look up his molar mass, it's 50.942 grams of vanadium for every 1 mole. And again, my grams go on the bottom to cancel. And when I do that math in my calculator, I need 4 sig figs in my answer. I get 0.006961 moles. I'm going to do the same thing for my oxygen. I've got 0.2784 grams of my oxygen. Every 1 mole of oxygen is 15.999 grams. My grams cancel, get me into moles, and that gets me to 0.01740 moles. So those are my subscripts in theory, but they're decimal places and we can't have that. So now we go ahead and we do step 2. This is our smaller number, so we're going to divide both these by that smaller number. This is going to get us 1V in our formula, but this is going to get us a different number. When we take our 0.01740 and divide it by 0.006961, you get this time an answer of 2.50. In my formula, I can't have VO 2.5. I can't have a decimal place as my subscript. So this is where step 3 comes into play. What I need to do is I need to multiply both these things by a number that can make this 2.5 a whole number. If we think about 2.5, it's really 5 halves. So I can multiply this by 2 to get rid of